Dear students, the topic is Galilean transformation. We are in the main topic relativity, special theory of relativity. The topic code is EMREL-S3. In Galilean transformation system, we consider two Cartesian coordinate system as shown in the figure, where system 2 has constant velocity v moving with a constant velocity with respect to system 1 in the direction of common axis, which is x-axis. Now considering the axes are parallel and are in the same direction. So here are two systems. This is system 1, which is represented by x1, y1, z1. This is system 2, which is represented by x2, y2, z2. System 2 is moving this one with a velocity, constant uniform velocity v. So neither system one moving with the system here, the two Cartesian system, one moving with velocity v with respect to the other in the positive x direction. The two systems are overlap when the origins O1 and O2 coincides. So neither is accelerated. Here the both systems are not accelerated. Okay, so neither system is accelerated. They are inertial frame of reference or systems. Now the two systems are related with the following relations: x1 is equal to x2 plus vt, while x2 is equal to x1 minus vt as per Galilean transformation. So here you can see this system 2 has traveled a distance which is x1 time. Here we have the x2 plus vt. So this is the total x1 distance. V with the velocity v, this has been traveling in the time t, v into t. So this much distance x2 distance plus vt, what we have x1 observer, if it is sitting outside and observing the system by the observer x1, it will see that the system 2 has traveled x2 plus vt distance, while x2 observer is sitting inside the system 2 will see that the distance is traveled by that system 1 is given by x1 minus vt. So this is total x1 distance, and this is the vt distance, the distance traveled by this system 2. So it will be the difference of these two, x1, that is, it will look like that the system is moving away from that the system 2. So that will be given by the x2 will be equal to x1 minus vt. Since there is no motion along the y1 z1, so y1 is equal to y2, z1 is equal to z2. Similarly, y2 is equal to y1, z2 is equal to z1. The motion is along x only. Now let's see now invariance of the second law of motion, F is equal to ma. Let us now write down the equations for the simple experiment that the passenger performs, first when the train is stopped and then when the train is moving with a constant velocity or speed. We shall see that the equation of motion in reference frame 1 are of the same as those of the in reference frame 2. Now let us consider that a passenger is given mass m, on which he exerts a known force F in the direction of the track by means of a calibrated spring. Here some passenger is there in this compartment. Calibrated spring in the reference frame 2. The reference frame 1 is fixed with respect to the ground. This one is fixed, and the reference frame 1 is fixed with respect to ground, and reference frame 2 is fixed with respect to the train. We assume that the force F applied is equal to f is equal to ma. As observed by the reference frame 1 observer, we deduce corresponding law in reference frame 2 when the train is stopped. We assume that the two frames overlap at x1 is equal to x2. Here x1 is equal to x2. So f1 is equal to ma1, f2 is equal to ma2. So let's say first we take f is equal to, putting that value of a1, which is d2x1 by dt square, will be equal to m d2x2 by dt square. In frame 2, this is frame 1. So f is ma applies in both the systems when the train is moving with uniform velocity. So then x1 is equal to, let's say now x2 minus x2 plus vt. Now putting this value of x1 in this equation first, so what we get, m d2 by dt square of x2 plus vt. So when we differentiate, now this v is the constant in that case. So here the what we get is the md2x1 by dt square is equal to md2x2 by dt square. Now if you differentiate twice these two terms, you will get from this md2x2 by dt square, while here the first differential will give you the v d by dt. V is constant, so the d by dt first differential will give you the v, and second differential d2 by dt square, the second differential, the v is constant, so it will give you the 0. So that is the second differential of this vt is equal to 0 since v is constant. So we are left with now, hence we have proven that the f2 is equal to f1. This law, that is the classical, the Newton's second law of motion, f is equal to ma, holds fine, applies in both the system. We therefore say that the law f is equal to ma of classical mechanics, classical physics, applies in both frame of references, or that it is invariant under the Galilean transformation. So similarly, we can show that f is equal to md2y1 by dt square, and f is equal to md2 d2 dy2 by dt square, as y1 is equal to y2. So with this we reach to the end of the topic. Thank you.